Hey, hey everyone, Professor Adjvan here. In this video, we're going to find intervals where a function is increasing and or decreasing, and we're going to do this utilizing a derivative. So we're going to do three examples in this video. The three examples are on your screen now. So if whatever you're currently working on look like these three problems, then this is the correct video for you. Alright, so let's go ahead and jump into it. So first of all, conceptually, why is a derivative going to help us find the intervals where a function is increasing or decreasing? Right, so we have a function, just a generic polynomial graphed, and we know that a derivative, a lot of people think it just means slope, but a derivative is specifically a function that will give you the slope of a tangent line at any given point. Okay, so if I was to draw a tangent line to this function at a bunch of different points, we would see that it is positive, meaning that this function is increasing, and then eventually it will become tangent lines that have a negative slope, meaning the function is decreasing, and then eventually this particular function switches back to having tangent lines that have a positive slope, meaning the function is increasing. Now something interesting happens when the function changes from increasing to decreasing or decreasing to increasing. We have these peaks and valleys. We have these maximums and minimums. So what's happening at these points? Right, well, if we have a tangent line on this point, the tangent line is going to be horizontal. Horizontal lines have a slope of 0. So if the derivative is going to tell us the slope of a tangent line at any given point, we can utilize this idea and find the derivative and find where it's equal to 0 to find like the break points, to find these maximum and minimums so that we can analyze what's happening to the left, right, in between them to find if our function is going to be increasing or decreasing. All right, so let's take this conceptual idea and apply it to some problems. All right, so the first thing that we want to do is just take the derivative. Right, so our first derivative applies the power rule. So I'm going to take the exponent and put it down in front, negative 2x. And then we have a coefficient times x, so the derivative is just going to be the coefficient. I want to take this derivative and set it equal to 0 to find where we're going to have those horizontal tangent lines. So we can subtract 2 from both sides and then divide by the negative 2 in front of x and get that x is equal to 1. So this is where the slope is equal to 0, the slope of the tangent line specifically. This number that we just found is also called a critical number. So what we want to do is take a number line, right? And 1 is our critical number, which means that 1 is where the tangent line is horizontal. And we now want to pick a test point. Anything to the left of -1, or excuse me, to the left of +1, or to the right of +1, right? So I can pick a test point, anything. I can pick 0, and then for this interval, I can pick something like 2. What I'm going to do with these test points is plug them into the derivative. So if I plug in 0, we end up getting 2. And we don't really care about the number so much as we care about the sign of the number. So this is a positive 2, which means that everything in this interval from -infinity up to 1 is increasing. We can do the same thing with 2. We can plug 2 in, -2 times 2 plus 2 is going to give us -2. Right, again, we don't care about the number so much as the sign in front of it. This is negative, which means everything in this interval is going to be decreasing. So for our original function, we can say it is increasing on the interval from -infinity up to 1, not including 1, and it is decreasing everywhere from 1, not including 1, up to positive infinity. Right, so that's the procedure. We take the derivative, we set it equal to 0, and solve for these critical numbers. And then we set up a number line with all of our critical numbers, and then we pick test points in all of those intervals, plugging them into the first derivative to identify the sign. If it's positive, it means that it's increasing on that interval. If it's negative, then that means it's decreasing on that interval. So let's try this process again with a different example. Let's look at this example where we have a binomial cubed. So to take the first derivative, we have to use the chain rule. So I'm going to bring the 3 down in front, take away 1 from the exponent, and then we multiply by the derivative of the stuff on the inside. So the derivative of x minus 2 is just 1, which is convenient. So if we simplify real quick, we have 3 times x minus 2 squared, and I want to set this equal to 0 to find those critical numbers. We can divide both sides by 3 to get rid of the coefficient. And if we take the square root to get rid of the squared, we have x minus 2 equals 0. So x equals 2 is our critical number. So what we're going to do again is set up this number line so we can identify some test points. I can pick anything to the left. So I could pick 1. I could also pick 0. I could even pick negative 10 if I wanted to. And then I have to pick 1 to the right. So I'm just going to pick 3. Because we get to pick the points that we want, it's advantageous to pick something like 0 that is typically easy to plug in. So we plug these points into the derivative, right? Not into the original equation, into the derivative, because I want to know what the slope of the tangent line at in this interval is going to be. So plugging in 0, we're going to get negative 2 squared, which is positive 4 times 3 is positive 12, right? Again, I don't care too much about the sign or about the number. I only care about the sign. So it's positive, which means we're going to be increasing on that interval. And I want to do the same thing with 3. We plug it into the derivative. Two squared is 4. 4 times 3 is 12. Right, we get positive 12. So again, this is positive, this is increasing. Right, so we can say that our function, the original function, is increasing on the interval from negative infinity up to 2, not including 2, and then also from 2, not including 2, to infinity. Right, we can put a u between them for the union, meaning we're bringing these two together. We cannot include 2 in this because 2 is a critical number. There's something happening at 2 that is making our derivative equal to 0. So in this third example, the first thing we want to do is rewrite it as 4 minus x squared to the power of 1/2, so that we can go ahead and take the chain rule derivative of it, meaning I want to take the 1/2 exponent and put it in front. Take away 1 from the exponent, 1/2 minus 1 is negative 1/2. And we need to multiply by the derivative of the stuff on the inside, so the derivative of 4 minus x squared is negative 2x. We can simplify this a little bit. We can cancel out a 2 and the 2 in the denominator from 1/2. So this is going to give us negative x divided by, because this binomial to the power of negative 1/2 is going to go on the bottom of this fraction, 4 minus x squared to the power of positive 1/2. So this is our simplified derivative, and we're setting it equal to 0. So I can easily multiply both sides by the denominator and get negative x is equal to 0, or x is equal to 0 as a critical number. Now up until this point, we've only had polynomials, and the critical numbers were always defined to be where the derivative was equal to 0. And that's still true. However, it's also, a critical number is also where the derivative is undefined. So we can find where this derivative is undefined by taking the denominator, 4 minus x squared to the power of 1/2, and setting it equal to 0. So if I square both sides, we have 4 minus x squared is equal to 0. Moving the x squared to the right, 4 is equal to x squared, and then square rooting, we'll have x is equal to plus or minus 2. These are also critical numbers. So in this case, we have 3 critical numbers, 0 from where the derivative is actually equal to 0, and then positive and negative 2 from where the derivative is undefined. So we want to take all 3 of these critical numbers, -2, 0, and 2, and put them on a number line and come up with some test points. So I need something smaller than -2. We'll use -3. Something between -2 and 0. How about -1? Something between 0 and 2. We can use 1. And something between 2 and infinity. We can use 3. You don't need to use these values. They just need to be some test point in these intervals. So we want to put all of these points into the first derivative. Right, so we have -3 over 4 minus -3 squared to the 1/2. Right, so this is going to give us a 3 on top, and the bottom is going to be 4 minus 9. So -5. And we're doing the square root of this. So what's happening here? Well, we are using a number that is outside of the domain, right? We're doing the square root of a negative number. We don't get an answer. So the function actually doesn't even exist over here. Picking something between -2 and 1, we picked -2 and 0, we picked -1. If I plug in -1 into the derivative, we have -1 divided by 4 minus -1 squared and 1/2. So in the numerator, we have 1 minus -1, which gives us +1. And in the denominator, we have the square root of 3. Right? I don't care what this number actually is. I know that it's going to be positive, which tells me that we are going to be increasing on this interval. I can also look at what happens when I plug in 1. So I have -1 over 4 minus 1 squared to the 1/2. So in the numerator we have -1, and we're going to get the same denominator as the previous when we plugged in -1. We're going to have the square root of 3. So now my answer is negative, so we are going to be decreasing on that interval. And then I can also plug in 3. However, when we plug in 3, we're going to see something similar happen, where in the denominator we have the square root of -5, which means it tells us that everything past +2 is not in our domain. So this function, it's only existing, and that makes sense if we analyze the domain of the function, it's only existing between -2 and +2. And in that time, it is increasing from -2, including -2, up to 0, not including 0, and decreasing from 0, not including 0, up to +2, including +2. Alright, so that is how we can use the derivative to find intervals of increasing and decreasing for any given function. If you found this video helpful, consider giving it a like and consider subscribing to the channel for more math content. Thanks for watching, good luck, and we'll see you in the next one.